Hello, my name is Aluna Everett, and today I will be presenting our paper enabling multi-material 3D printing for designing and rapid prototyping of deformable and interactive wearables. This work was in collaboration with Alexander Keith Eady and Audrey Girard. Within the HCI community, research on wearable devices is growing as we begin to explore a wide range of forms, interaction techniques, sensing capabilities, and visualizations. We are also starting to cover a broad range of applications, including sports and performance monitoring, healthcare, fashion, and workwear, just to name a few examples. With a wide range of applications come design challenges for conceptualizing, developing, and testing devices that can be easily worn on the body, follow movement, and/or attach to existing garments. As a result, there is a growing interest for fabricating deformable wearables with stretchable surfaces that can adapt to the body and movement. As the domain of wearables matures and expands, we see the need to further support the design and development of wearable technologies, and particularly with rapid prototyping approaches. One of the most common ways of prototyping and developing wearable and mobile devices is using e-textiles, which comprise of electric components directly incorporated with fabrics using conductive thread to create interactive surfaces. As seen by projects such as Jakarta and Resi, you can see that on the top right of the screen, e-textiles can easily support touch interaction capabilities for conductive yarn and thread directly sewn on textiles and garments. We are now also starting to see more toolkits for prototyping e-textiles, as demonstrated by Wearable Bits by Jones et al. However, e-textiles usually require fabric and garments for the electronics and for the functionality to be embedded with. And most commercially available fabrics are difficult to customize, particularly in terms of stretching and deformation factors. Alternatively, we're also starting to see more thin on-body devices for on-skin interaction, as seen by stretches and duoskin at the bottom of the screen. These prototype thin skin overlays support stretchable wearables devices and can often be considered as interactive skin-on tattoos. The thin skin overlays, such as stretches and duo, can support display output and deformation sensors and context body posture, depending on controls. But they do require multiple layers of chemical compounds such as P.PSS for printing and masking for conducting polymers. We are now also starting to see greater demand for highly customizable and stretchable devices. Work such as electrodermis is enabling the prototyping of large range of customizable wearable skin-on devices, which can support multiple features and applications such as forehead monitoring, human motion tracking, and even food detection through a necklace. However, as you can see, there is a particularly detailed diagram of the fabrication process, and they require a large number of steps and specific equipment such as UV laser micromachining. These are required to create one of these multi-layered devices, and you really need to have specific technical skills and materials to be able to try and recreate one of these, and particularly in a lab setting. You can also see the multiple layer approach is used for constructing stretchies, the on-skin user interfaces that we saw earlier. And though this approach does require more simple tools and techniques for prototyping, such as masking and a heat gun, you would have to have a range of specific materials such as PDMS, on phosphor for visualization, and other conductive materials. As a result, we propose a more simplified rapid fabrication technique that utilizes multi-material 3D printing for developing customizable and stretchable surfaces for mobile wearables with interactive capabilities embedded during the 3D printing process. And though there are still some hands-on assembly required, particularly for embedding LEDs, generally this is very straightforward. And our main research question and motivation to explore is to actually understand how multi-material 3D printing can better support the fabrication and the prototyping of these deformable wearables. And our main contribution is our simplified rapid fabrication approach that utilizes multi-material 3D printing for customizable, stretchable, and interactive wearables. Our main contribution is our fabrication approach and our pipeline, which consists of 5 steps, which I will go into more detail during this talk. But as an overview, the first step is to design the surface using CAD software, such as Fusion 360. The second step is to 3D print the surface using a multi-material 3D printer, such as the Ultimaker 3. And steps 1 and 2 are iterative, so a user, if they're not happy with the 3D print, they can go back to the 3D model and adjust the design as required. In step 3, we assemble the electronic components using conductive thread to create an electronic circuit to enable interaction and visualization capabilities. In step 4, we program the functionality using a microcontroller, such as an Arduino or even an Adafruit Gemma. And finally, once we are happy with the surface and its functionality, we can attach it to the body or a garment or even a mobile object using double-sided tape or even pins. So the surface of the device itself consists of 3 main components. There is the black conductive material, which you can see, and this enables capacitive sensing and the interaction functionality. There is also the white material, which is flexible and supports stretching and deformation of the surface. And finally, we have the embedded electronics, such as LEDs, which can support the visualization function. In the first step, we design the surface using an array of tiles, which are connected together using links, as you can see from these 2 3D models. Each tile has a gap in it to situate an electronic component, such as an LED, and once you have the design of 2 tiles and 2 links, you can just copy and paste them into an array of your shape and size. In the initial design explorations and tests, we 3D printed a range of tile shapes and found that most shapes work well as long as they can house the electronic components you wish to embed later on. For our prototype, we also chose to use squares, and we later explored which link design is most appropriate to achieve stretching and folding of the surface. We found that the S-shape link attached horizontally to the tile works best for achieving maximum stretch length and folding, and our designs were very much inspired by Oxetics. Here you can see the final link and tile design, which provides the greatest stretch and folding capabilities that we have found so far. This is a full 3D model of one of our prototype surfaces, consisting of a 5x9 tile array. The 3 small gaps within each tile is used to thread the conductive thread through, and the larger gap is used to situate the NeoPixel LEDs. You can find this 3D model and a smaller one with just 2 tiles, which you can create your own specified array or design with in the supplementary materials. The 3D printing process itself is pretty straightforward, and for our work we use an Ultimaker 3 with dual extrusion, and you can find more details about the printing settings in our paper. But to summarize again, for the materials that we used Protopasta electrically conductive PLA, which is the black material, which is conductive, and we use the Cheetah Snow White TPU as the flexible material. For the electronic components, we use Adafruit LED sequin, which can be purchased in single colors, or an Adafruit Flora RGB LED, where an additional data in and out pin can support multicolor and brightness control sequentially. We also connect the circuit using conductive thread, which we insulate using clear nail polish, and for the microcontroller, we can use either an Arduino Nano or an Adafruit Gemma. And to enable capacitive touch sensing, we have an Arduino capacitive sensing library, which you can find a link in our paper for, and a resistor which is connected to a data pin. At the bottom of the screen, you can also see the diagram of the circuit setup that we used. We specifically decided to use LEDs, which we designed for wearable applications, as they are easier to connect using conductive thread with their specific pinholes. Once you have placed each electronic component into its designated gap in the tile, you can simply thread the conductive thread through each RGB LED, and to ensure there is no issues with short circuiting or cross wiring, we insulate the conductive thread using clear nail polish, which works very well as an insulator for conductive thread. In terms of programming, we utilize the Arduino IDE and its many libraries, such as the capacitive sensing library, in conjunction with a medium to high value resistor connected to a conductive filament to enable touch sensing. We set a range of thresholds for the capacitive touch sensing to detect how hard a user is pressing on the surface. The higher the reading, the harder the press. Once the surface is fully assembled and functioning, it can be attached to the body using double-sided tape, attached to clothing using pins, or other objects using conventional double-sided tape or even super glue. The device can also be secured onto the hand like a bracelet using clips, or secured to other clothing and garments directly by sewing it with thread. Our prototype surface can support a set of interaction capabilities from touch, bending, and stretching. We can also demonstrate device body placement as we show our prototype as a hands-worn device that wraps like a glove around the wearer's hand, and also as a knee bend sensor attached to a pair of ripped jeans. Touch interaction is supported for conductive filament tracks that span each row of the tiles that can detect a change in capacitance when the user's finger is closer to the conductive filament. Deformation detection is also shown, as the device can support and adapt to bend and stretch of the body with electronic circuits embedded within it still. Using capacitive input from the conductive material, we can detect a human limb flexing and bending based on the proximity of the skin to the conductive tiles when the surface is stretched over a joint like the knee or the elbow, for example, as we can see in the video. And finally, we can support on-body interaction where we can detect when the surface is not worn on the body. So, for example, when the prototype is placed on a non-conductive table, such as a wooden table, the capacitance sensing will be low. Once the surface is placed on the skin, there is an increase in capacitance from the conductive filament, making closer contact to the skin. And this enables the device to distinguish between worn and not worn, and how it could be used to control device modes, for example, so that the device can go into a power-saving mode when it is not actively worn. In terms of application scenarios, we envision our fabrication approach being utilized in areas such as digital health and more specifically physiotherapists to help support their patients when they are performing stretches and exercises on their own. In the future, we would also like to run in-depth co-design workshops with physiotherapists to better understand how the devices we design and build using our fabrication approach can help with current challenges in their domain. Additionally, we also aim to look into sports and performance monitoring. This is a common application area for wearables. However, there is little work that looks into how knee bend monitoring, for example, can better improve performance and reduce the risk of injury in weightlifting exercises such as deadlifts and squats. We aim to run a usability study with gym goers to see how our fabricated devices can potentially monitor user perform during squats and provide real-time feedback on their performance. To demonstrate the potential for replicability of our fabrication process, we built 25 prototypes in total, 21 of which have been used as toolkits for Master's remote workshop in prototyping wearable technologies. Each prototype packed and was sent to students' homes from the UK and also around Asia and Europe. Each student was able to set up and assemble the prototype during a Zoom workshop without any electrical failure, and we believe this can demonstrate the robustness and replicability in the nature of our prototypes. In terms of future work, we would like to create more user-friendly design tools and plug-in widgets, much like Morphe's Plug by Kim et al., which can be used by those who are not familiar with 3D modeling, for example. And we would also like to integrate a wider range of sensors and new electronic components, such as light sensors, temperature sensors, accelerometers, just to name a few. There is also great potential to explore self-actuated wearables using actuation techniques such as pneumatics or even shape memory alloys. And in terms of scale, there are other form factors that we need to explore, such as large-scale prototypes. Though at the moment we are currently limited by the size of the print bed, we can attach multiple surfaces together to make one larger one, or even explore smaller scale surfaces potentially. And as we've mentioned previously, we're also focusing our future work on usability testing in the domains of sports and performance monitoring, and we're also hoping to see our fabrication approach utilized in digital health applications. Overall, the main goal of our work was to provide a rapid prototyping platform and allow and encourage others to take advantage of it for designing and developing new mobile and wearable devices of their own. We would like to thank you for your time and we look forward to your questions.